Why is it so hard to get to Jupiter's moon Europa? Europa, a moon orbiting Jupiter, is a fascinating place. Discovered by the astronomer Galileo Galilei in 1610, it's one of Jupiter's biggest moons. Researchers were astonished to discover that Europa possesses an extensive ocean hidden beneath its icy exterior. This makes it an interesting spot to look for alien life. But here's the thing. Even though Europa could be home to strange creatures, we haven't been able to send people there to check it out. Why is it so tough to reach this distant, icy moon? Stick around as we dive into the reasons why Europa remains an elusive destination for space explorers. Pioneer 10's epic voyage. The Pioneer 10 mission, launched on March 2, 1972, marked a significant milestone in space exploration. It was the first spacecraft to traverse the asteroid belt and make direct observations of an outer planet, specifically Jupiter. The mission's primary objective was to study Jupiter's atmosphere, magnetosphere, and satellites, particularly Io, as well as solar wind parameters and dust distribution. Equipped with a suite of scientific instruments, Pioneer 10 was designed to unlock the mysteries of the gas giants, about which little was known at the time. The spacecraft was propelled by NASA's Atlas Centaur rocket, which provided the necessary thrust to send it on a trajectory towards Jupiter. This trajectory was carefully planned to take advantage of a rare planetary alignment, allowing the spacecraft to use Jupiter's gravity as a slingshot to reach the outer solar system. The Atlas Centaur rocket accelerated Pioneer 10 to a speed of 51,682 kilometers per h, or 32,114 miles per hour, making it the fastest human-made object at that time. As it journeyed through the Van Allen radiation belts, several onboard instruments were activated to perform tests, providing valuable data about this region of space. Upon reaching interplanetary space, Pioneer 10 continued its journey towards Jupiter. On December 3, 1973, it made its closest approach to the gas giant, becoming the first spacecraft to explore Jupiter up close. During this encounter, Pioneer 10 also observed Europa, one of Jupiter's moons. The data sent back revealed that Europa was a much more complex world than previously thought, hinting at the moon's potential geological activity and the presence of a subsurface ocean. Following Pioneer 10, the Pioneer 11 mission also made significant contributions to our understanding of Jupiter and its moons. Launched 2 years later, Pioneer 11 captured new images with better definition, further enhancing our knowledge of these distant celestial bodies. The Voyager missions, which followed the Pioneers, provided even more detailed observations of Europa. Voyager 2, in particular, offered the first images that were close enough to reveal that Europa's surface is crisscrossed by ridges and cracks, suggesting that the moon might be geologically active today. The subsequent Galileo mission provided the strongest evidence yet of an ocean beneath Europa's icy crust. These missions collectively contributed to our current understanding of Europa as a potentially habitable world with a subsurface ocean that could harbor extraterrestrial life. The data gathered by Pioneer 10 and 11 laid the groundwork for these later discoveries, demonstrating the importance of initial momentum and planetary alignment in space exploration. The roughly 13-month gap between Earth and Jupiter provided a window of opportunity for these spacecraft to embark on their historic journeys. Voyager and the Grand Tour program, the Pioneer 10 and 11 missions indeed exceeded expectations, serving as pathfinders for the more advanced Voyager probes. The Grand Tour program, which aimed to explore the outer planets, was ambitious and costly. The program's initial budget of about $1 billion was significant for its time, leading to its cancellation and the inception of the Mariner program, which evolved into the Voyager mission. The Voyager spacecraft were equipped with cutting-edge technology. They carried more fuel and had longer-lasting batteries, allowing for extended scientific observations with sophisticated instruments. Voyager 1 and 2 were launched in 1977, with Voyager 1 reaching Jupiter in January 1979 and Voyager 2 in July 1979. Despite taking longer to reach Jupiter due to their heavier payloads, the Voyager probes made groundbreaking discoveries. They provided the first high-resolution images of Jupiter and its moons, transforming points of light into worlds with weather, volcanoes, and tectonics. The Voyager's exploration of Europa was particularly significant. The moon's high albedo suggested the presence of ice, which the Voyager images confirmed. These findings sparked great scientific interest, as Europa's icy surface and potential subsurface ocean made it a prime candidate for harboring life. The historical context of these missions is crucial. The costs and challenges of space exploration programs have always been substantial, but the benefits, in terms of knowledge and technological advancement, have been immeasurable. The Pioneer and Voyager missions paved the way for our current understanding of the solar system and continue to inspire future explorations. Secrets of Jupiter's mystical moon. The Pioneer and Voyager missions indeed were designed to capitalize on a rare planetary alignment to explore the gas giants and potentially exit the solar system. During their voyages, they provided groundbreaking data about Europa, one of Jupiter's moons. Europa's surface was found to be remarkably smooth and youthful, with fewer impact craters than expected. This indicated that some form of geological activity was resurfacing the moon, a phenomenon not previously observed on other moons. The leading hypothesis for this activity includes the possibility of a subsurface ocean exerting tidal forces that reshape the surface. The Hubble Space Telescope played a pivotal role in furthering our understanding of Europa. It detected signs of water vapor plumes near Europa's south pole, suggesting that the moon might harbor geysers capable of reaching the surface from the subsurface ocean. This discovery was significant as it was the first time water was detected on a body other than Earth within our solar system. The presence of water on Europa has shifted the focus of exploration missions. The moon's potential subsurface ocean makes it a prime candidate in the search for extraterrestrial life. This has led to the prioritization of Europa as a target for future missions, such as NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moon Explorer JUICE. These missions aim to investigate Europa's ice shell, subsurface ocean, and overall habitability, furthering our quest to understand whether life exists beyond Earth, probing Jupiter and beyond. The Juno mission, often mistakenly referred to as Juno, is a pivotal NASA mission dedicated to the exploration of Jupiter and its moons. Launched on August 5, 2011, the Juno spacecraft embarked on a journey to delve into the mysteries of Jupiter, the largest planet in our solar system. The travel time for Juno to reach Jupiter was indeed longer than that of its predecessors, the Pioneer and Voyager probes. This extended duration can be attributed to several factors, including the spacecraft's weight. Juno weighs approximately 7,991 pounds, which is significantly heavier than both the Pioneer probes, which weighed around 568 pounds, and the Voyager probes, which weighed between 1,620 pounds and 1,796 pounds. The weight of a spacecraft is a critical factor in determining its travel time because it directly influences the amount of fuel required for propulsion. In space, the absence of friction means that spacecraft can coast at constant speeds after their engines are shut down following the initial boost. However, the gravitational pull of the Sun and other celestial bodies can slow down a spacecraft, necessitating additional fuel for heavier spacecraft to overcome this gravitational pull and maintain their trajectory. Juno's journey to Jupiter also involved a carefully planned route that included a gravity assist maneuver from Earth, which occurred on October 1, 2013. This maneuver was designed to increase the spacecraft's speed without using additional fuel, leveraging Earth's gravity to slingshot Juno towards its destination. The intricacies of space travel, such as the gravitational forces and the need for precise navigation, make missions like Juno's both challenging and fascinating. Juno's successful arrival at Jupiter on July 4, 2016, and its ongoing exploration of the gas giant and its moons continue to provide invaluable insights into our solar system. As for human-crewed spacecraft, the considerations for weight and travel time become even more complex. The need for life support systems, additional safety measures, and the comfort of the crew all contribute to a significant increase in weight, which would indeed result in longer travel times and more complex mission planning. Challenges of interplanetary voyages. Using today's most powerful rockets, a manned spacecraft wouldn't be able to reach speeds sufficient for a journey from Earth to Jupiter in under 5 years. A conservative estimate suggests that a spacecraft at least 3 times larger than the Apollo craft that landed on the moon could, at best, cover this distance in 8.5 years for a one-way trip. This implies a round trip would take 17 years. Which is unfeasible due to the need for extensive supplies like food, water, and fuel. Carrying such heavy loads would further increase travel time. Clearly, a voyage to Europa using current technology is not viable. To make such a lengthy journey feasible, astronauts could make short stops at other locations like the Moon, Mars, and Ceres, a dwarf planet in the asteroid belt. Establishing bases on these intermediary celestial bodies could significantly reduce travel time by lightening the spacecraft's load and allowing for faster travel speeds. The vision of establishing a network of bases within our solar system is a bold leap into the future of space exploration. This concept, often referred to as the stepping stone approach, envisions a series of outposts from the Moon to Mars and beyond, serving as relay points for resources and refueling, much like pit stops in a cosmic race to the outer planets. The Moon, our closest celestial neighbor, presents a logical first step in this journey. With projects like NASA's Artemis program aiming to land humans on the Moon this year, the idea of a lunar base is not far-fetched. Such a base could utilize the Moon's resources, like water ice, to support life and potentially fuel rockets using hydrogen and oxygen derived from the lunar regolith. Mars has been the subject of numerous missions, with rovers like Perseverance searching for signs of past life and preparing for future human exploration. A Martian base could exploit local resources, such as water ice and carbon dioxide, to sustain human presence and create fuel through processes like the Sabatier reaction, which produces methane and water from carbon dioxide and hydrogen. Ceres, the dwarf planet located in the asteroid belt, offers a unique advantage due to its abundance of water ice, which could be used for life support and fuel production. Its position also makes it an ideal waypoint for missions aiming to venture deeper into the solar system. The concept of spacecraft refueling at these bases aligns with the idea of in situ resource utilization, ISRU, which is crucial for sustainable space exploration. By using resources harvested at each stop, spacecraft can significantly reduce the amount of fuel and supplies needed to carry from Earth, making long-duration missions more feasible. The journey to Europa, one of Jupiter's moons, would indeed be a monumental task. Europa is of particular interest due to its subsurface ocean, which could harbor extraterrestrial life. However, reaching it within 1.5 years, as proposed, presents significant challenges. The alignment of celestial bodies is one such challenge, as it affects the trajectory and speed of interplanetary travel. While the current technology does not allow for such rapid transit, advancements in propulsion systems and space travel infrastructure may reduce travel times in the future. The return trip from Europa would require careful planning, as the alignment of planets would have shifted, necessitating either a longer stay on Europa or a different return trajectory. This highlights the importance of understanding orbital mechanics and having flexible mission plans. While we are still in the early stages of making such a sophisticated network of space bases a reality, the progress in space exploration and technology gives us hope that one day such interplanetary travel could become routine. Until then, each mission brings us closer to understanding what it will take to become a multiplanetary species. Intrigued by the hurdles in exploring Europa? Comment your thoughts below and hit like and subscribe for more insights on space exploration.